Integrated circuits, or microchips, have drastically changed the electronics industry
Is it okay if I use your phone real fast?
and the way we do things.
Voice console. Wake up.
They run the computers
Hello.
and sophisticated electronics,
My name
which are now a
is
part of
Mike.
our daily lives.
Period. Go to sleep.
The manufacture of electronic products has grown into a major industry. It involves billions of dollars and millions of people worldwide.
Leave us a message. We'll get back in touch.
Electronic products work because of the integrated circuits inside. These microchips are made up of microscopic electrical devices that direct the flow of electricity. Working together, these devices store data, make calculations, and generate signals. Before integrated circuits existed, products were bigger because electrical devices were individually wired together as bulky circuits. This changed when the modern electronic era bloomed. Thousands of transistors and other electrical devices were integrated on a small slice of silicon crystal. Today's microchips contain millions of transistors. Looking inside a computer, we find rows of these microchips. Each one is capable of storing information or executing hundreds of millions of operations per second. The bulky vacuum tubes of the past were replaced by the individual transistors. These have evolved into the integrated circuits fabricated around the world in technological centers like Silicon Valley. It all begins with the growth of pure silicon crystals. Silicon is the common element found in sand. It is 28% of the Earth's crust and second only to oxygen in abundance. The silicon from the sand is refined and purified into silicon chunks. This purified silicon is then heated to a molten state. Here we see a small crystal called a seed being gently lowered into a rotating vat of molten silicon. When the seed touches the hot liquid, the surrounding silicon begins to cool and solidify, copying the seed's atomic structure. The seed is gently pulled from the hot molten region as a new crystal forms. After 48 hours of growth, this is what a single silicon crystal looks like. Silicon is known as a semiconductor. It has the unique ability to be a good conductor of electricity or a poor conductor. This depends on the type and concentration of elements added to the silicon. After the heads and tails of the crystals are removed, the shiny rippled surface is ground smooth. Diamond blade saws cut the smooth crystal into wafers that are as thin as possible without being too fragile and difficult to handle. The final polish is done on only one side of the wafer. The characteristic mirror-like luster is free from scratches and contamination. This machine is measuring and testing the wafers so they can be sent to manufacturing sites where they will be made into integrated circuits. Meanwhile, hundreds of specialists are working together to design the circuits that will be built on the wafer's surface. Computer architects are the idea people. They decide what the chips will do. Logic and circuit designers work out the architect's ideas and produce a circuit schematic.
Let's look at this inverter.
Mask designers convert the circuit schematics into the actual patterns that will be transferred onto the wafer's surface. They produce a master blueprint, usually 400 or 500 times the actual size of the chip.
That area definitely.
The design is a maze of interconnected microscopic transistors.
Is easily within 50 microns.
A transistor is like a tiny switch that controls the flow of electricity. It turns on and off hundreds of millions of times per second. Transistors are built at a microscopic level on the surface of the wafer. This cross-section overview of the process shows the step-by-step creation of 2 transistors. There are millions of these transistors in the master blueprint. Imagine the wafer is as thick as a 100-story building. The millions of transistors in the circuitry are built only on the very top floor. The 2 yellow regions in this transistor are areas where elements with lots of extra electrons have been added. These conductive regions become the ends of an electronic switch, which is normally off. When a positive voltage is added nearby, opposites attract, and electricity flows through the transistor. The switch is on. This on and off is the 0 and 1 that makes up the digital code used in modern electronic communications. It is the language that computers understand and translate into useful operations. Let's go into a laboratory and see how these integrated circuits are made. The actual manufacturing process requires an ultra-clean environment. Control of contamination is extremely important. One source of contamination is the human body. Oil, salt, dry skin cells, and hair are kept away from the wafer's surface by the special clothing that technicians wear. From start to finish, the complete run or manufacturing process may involve hundreds of individual steps and take weeks to complete. The equipment, gases, and chemicals that come in contact with the silicon wafers must also be of the highest purity. We begin the run by cleaning the wafers in hot acids: hydrochloric acid, sulfuric acid, hydrogen peroxide, ammonium hydroxide. That's what it takes to remove all the contaminants. We repeat this cleaning procedure over and over again throughout the process to make sure the surface of the wafers stay absolutely clean. The wafers are rinsed in deionized water and spun dry in filtered nitrogen gas. In a furnace, high temperatures form thin layers of silicon dioxide, a glass-like insulator which protects the silicon beneath it. The silicon dioxide layer will be etched and used as a stencil, so specific regions of the wafer can be treated. The pattern for the stencil comes from a carefully designed mask. Each mask represents one colored layer from the master blueprint. This machine etches each layer onto chrome-plated glass plates. After the glass plates are etched, they become the masks or stencils that will be used to pattern each layer of the integrated circuit. Most integrated circuits use from 12 to 25 masks, depending on the complexity of the circuit. Each pattern is transferred from the mask onto the wafer using a photographic process. a light-sensitive substance called photoresist is spread over the surface. Then the wafer enters a machine called a stepper. Inside the stepper, the appropriate mask is selected and the wafer is positioned underneath it. Ultraviolet light exposes the photoresist through the mask. In this way, we can create many chips on a single wafer. When the wafers are developed, the exposed photoresist dissolves, leaving the mask pattern on the surface. Some areas are protected by the photoresist, and others are not. The regions of silicon dioxide that are not protected by photoresist are etched. The resist is removed and a stenciled silicon dioxide layer is left behind. To make these unprotected areas more conductive, we add selected elements. In a hot furnace, these added elements are driven deep into the wafer's surface to create richly conductive wells, where one of our transistors will be built. A layer of insulation is then deposited, and we are now ready for the next mask. Photoresist is again evenly spread on the wafer. This photographic process will be repeated over and over again with each mask, so different layers of deposited materials can be patterned. This technique allows us to block specific areas of the surface while others are being worked on. In this way, we can build and etch using layers of materials. Conductive regions are formed and insulated from each other. Later, they are selectively connected to each other to produce the integrated circuits. After several masks, the transistors are almost complete. A thick insulating glass layer is deposited. After so much layering, the surface of the wafer is no longer level. This bumpy surface can create out-of-focus mask transfers. To make sure that the remaining mask transfers are in sharp focus, the surface must be leveled or planarized. This creates the flat surface required to produce precisely detailed patterns. The next mask defines the openings through which the metal wiring will be able to contact the transistors. By etching the unmasked portions, contact holes are created. Through the microscope, we can see these holes as small dots. A combination of tungsten and aluminum are then deposited onto the wafer. The next mask patterns the aluminum into microscopic wires. These narrow metal strips extend from one transistor to another and form the first layer of wires connecting the circuitry. In sophisticated circuits, the wiring is so complex that it's impossible to complete with a single layer. This highly magnified photograph shows a device with 2 layers of wiring. This cross-section shows 5 layers. Each additional layer typically requires at least 2 additional masks. After all the desired levels are in place, a final layer of insulation is deposited to protect the fragile aluminum wiring. In the last photolithography step, small pads along the edge of the microchip are left exposed. These white aluminum pads are the contact points between the microscopic wiring of the integrated circuit and the outside world. The wafers are then stripped of photoresist, and the run is complete. Despite the care taken in the fabrication process, not all the chips on the wafer work. Now the individual chips on the wafer are tested. Here we see wire probes touch each of the small pads to make sure electricity is flowing through the circuit. This inking machine marks each failed circuit with a black dot. Soon the wafer will be cut into individual chips. A sticky blue mylar tape has been placed on the back of the wafer so the chips stay in place while they are cut. In soapy streams of water, a diamond saw cuts through the silicon wafer without cutting the tape beneath. The chips on the wafer are separated, but they stay attached to the tape. A camera scans the individual chips. The electronic eye detects the ink blots that mark the failed chips and skips them. The good chips are removed. The tiny fragile chips need a protective frame. These metal strips will be their protective housing. Here we see the small integrated circuits being glued to the metal strips. A gentle scrubbing motion ensures a good contact. This high-temperature oven hardens the glue. Now the metal frame must be connected to the small aluminum pads on the integrated circuit. In slow motion, we see the thin gold wire connect from the pad to an individual pin on the frame. These pins are now attached to the microscopic circuitry of the integrated circuit. To further protect the chips and their fragile wire bonds, the devices are encased in hard plastic. After several minutes, the encapsulation process is complete. The chips will eventually be soldered to a printed circuit board. In order for them to attach properly, the pins must be thoroughly cleaned and then plated. Next, the strips are cut and the tiny pins are bent so they will sit properly on the printed circuit board. Quality control is very important. Before the chips go any farther, they are tested. They are loaded onto test boards which will be placed in ovens. On these boards, the chips will be electrically stressed far beyond normal conditions. Weak chips are forced to fail before they're put into a customer's product. In rows and rows of test ovens, the chips are powered up and exposed to high temperatures for several hours. In another test, the chips are exposed to contrasting cold and hot temperatures. An electrical socket then tests each pin. The chips are sorted according to those that meet the highest requirements, those that meet lower requirements, and those that have failed. We mark the chips that pass with the manufacturer's logo. They are visually inspected, laser marked, and packaged for distribution. The printed circuit board allows many chips to communicate with one another and with the outside world. Signals travel between chips along electrical pathways on the circuit board. The maze of electronic pathways is created by circuit board designers who find the most efficient way for the signals to travel. These designs are transferred onto the bare printed circuit boards. Let's follow the assembly line and see how a complete system, such as a computer, is actually made. Much like screen printing, solder in the form of paste is pressed onto the board through a brass stencil in the areas where microchips will be attached. Each microchip is automatically positioned where the solder paste was deposited. Now the boards go through an infrared oven. The solder melts and bonds the microchips to the top side of the board. Tiny chips are temporarily glued to the bottom of the board until they can be soldered later in the process. The other way of placing parts on the board is the through-hole assembly process. Here, electronic components with straight pins are inserted through holes in the circuit board. The wires are then clinched from underneath to hold them in place until they are soldered. This eyelet setter, or rivet press, secures any large connectors located at the edge of the board which need extra strength. The circuit board now contains all of its components. An operator makes a final visual check. A wave solder machine does the final soldering. The bottom of the board is first coated with solder flux. This substance prepares the pins so the solder will adhere correctly. From beneath, we see the hot solder just touches the small wire pins. Next, we test the boards and send the good ones to system assembly. We place the boards in a computer casing. The speaker assembly and the data cables for the disk drive are attached. The disk drive mounting bracket with the floppy drive is inserted. The hard drive snaps into place and the drive power and data cables are connected. The power supply for the computer is installed. The system is fired up to prepare it for the first phase of testing. Additional temporary memory and test cards allow software to exercise all areas of the system. We monitor the testing and verify that the system is running correctly. The test cards are removed, and the assembly of a personal computer is complete. And me? I'm ready for my own kind of run.